Getting started. So welcome to the Tech Talk of the Innovative Discovery Series. This is kind of a few housekeeping announcements. I'm going to do my best to imitate Claudine, but I do not have the beautiful French accent, so you'll just have to go. So for CME credit, you must sign in and must include your email and credentials. Don't miss our April 4th Tech Talk with Parth Patel from the University of Delaware. Title forthcoming. I know you're all excited. Also, please note March 15th ID series. We'll have Dr. Shannon Lendon Edwards from the University of Delaware speaking on diet and vascular function. Please register for that to help us prepare. And the full schedule is posted on our website, DE-CTR.org. All right. So this afternoon, it is my pleasure to introduce Dr. Jihad Obeid. Did I say it right?
Obeid.
Obeid, sorry. We'll be talking about deep learning for text classification in electronic health records. Dr. Obeid is the co-director of the Biomedical Informatics Center at Medical University of South Carolina, and a pediatrician with formal training in medical informatics. He leads efforts on multiple research informatics projects, such as the Research Data Warehouse, I2B2, REDCap, and many others. He's a principal or co-investigator on several NIH-funded projects, and his research interests include secondary use of EHR data for research, electronic consents, research permissions, and machine learning. Take it away, Jen.
Oh, okay. Thank you for the introduction. I've been asked to do a presentation on so-called TensorFlow, but I think since many of you don't know what that is, we changed the title to deep learning, which is what TensorFlow is used for. Deep learning for text classification in electronic health records. And I'll explain what that is in a minute. I'm going to start with a brief machine learning primer just to make sure we're all speaking the same language, and then talk about the different research projects we're doing in this area. And please feel free to stop me if you have questions or if you can't hear me for some reason or anything like that. Some of you may know this, but machine learning is not a new field. It's been around for quite a while, since the 1950s. The person who first coined the term was Arthur Samuel. He was a professor at Stanford, and he was working in gaming programs like checkers, teaching the computer to learn checkers. Some more modern examples of machine learning applications to demonstrate what we mean by the ability to learn by a computer is, the typical spam filtering, which is instead of having programmers program the actual rules for detecting spam, like certain words. Instead, you teach the machine or the algorithm to read the different, many different texts, and then learn which ones are spam and which ones are not by statistical machine learning. So there are different types of machine learning. Supervised and unsupervised are the two big categories. There are other categories as well. But in supervised machine learning, the point is that you have to have a set of known observations with what's called responses. So both the independent variables and the outcomes of the independent variables. Here are some examples, like predicting renal failure in patients with diabetes, predicting cancer based on clinical and genetic factors. So it's similar to like statistical predictive models as well. Some of the predictive models are actually types of machine learning models. And then you have unsupervised machine learning. These are things like clustering algorithms where you can identify classes of different categories automatically without any given responses or labels. Some examples of supervised machine learning. Here's one that you can find out in the wild quite a bit, like prediction of survival on the Titanic. Here's an example using a decision tree as a machine learning model. Logistic regression is another example, a very simple example that predicts, it's a simple classifier that predicts yes or no as an output. Then you can get into slightly more advanced methods like artificial neural networks, which are basically interconnected nodes. Each of them has a different type of activation. Usually, nodes can have either a logit function that activates the nodes to make it. And if you put them together, then you can come up with more complex predictions. So it's a little more advanced than logistic regression. So some activation functions include like the logit function, which is a sigmoid, and something called like it's called a rectified linear unit, which is very often used in the hidden layers of a neural network, and softmax, which is used for multi-class classifiers. Also, a very high overview of what we mean by these different terms here that you see, artificial intelligence, machine learning, and deep learning. So artificial intelligence is the overarching field, which is a subfield of computer science that covers machine learning and many other things like natural language processing, all forms of it, and other types of computer reasoning that doesn't have to necessarily be based on statistical machine learning models. Machine learning then is a subset of AI, and the idea there is that the algorithms perform the tasks based on the patterns that they learn from the data. And then deep learning is a subset of machine learning, and it's become much more popular in recent years because of the advancement in computational power and libraries that have come up that made it easier to use deep learning. And so what we mean by deep learning is that basically here you're using deep neural networks simulating how the brain works somewhat. And they're heavily used in things like computer vision, speech recognition, and more advanced NLP, or natural language processing. Here's an example of a deep learning model. This one is for computer vision. You might have seen this out there on the web, where computers are learning to read or to identify images or identify face recognition. This example is about face recognition. And the advantage of having a deep learning model is that the learning is segmented over several networks or layers of networks, where you start recognizing the edges in the first part, then you start recognizing parts of the face in the second layer of networks, and then you can in the end have a whole face recognition and the output. So just some differences in vocabulary between statistics and machine learning. So we tend to use the word features when we're talking about predictors or independent variables. In machine learning, we also tend to use the word labels for the outcome variable. So you often hear people talking about labeled data. That means you have the answers already, and that's used for supervised machine learning. Also, what we mean by a classifier, actually, this is not unique to machine learning, but a classifier means that it's an ordinal response or output. Could be multi-class or a simple yes/no binary classifier. and regression is a continuous variable output. And the way we train machine learning models is that we divide the data into training data and testing data. And then the training data is used for both training and validation while you are training. So you may hear the term k-fold or tenfold cross-validation, where part of the data is set aside for just seeing how well the model is learning as you propagate through the learning cycle. And then you hold out a set called the testing set, which is not supposed to be seen during the training. And you use that then, the test set is what is used to assess the performance of the model. So it's either called a test set or a holdout set. And you could also, sometimes you may, if you don't have a large amount of data, you may have to repeat the training and testing several times using something like k-fold, but instead of just doing one experiment, so you could do 5 experiments and then take the cumulative or pooled results to assess the model. Okay, so the work we do, the work I'm doing is focused more on text classification, and you may be familiar with text classification in places like Google or Amazon, where they use classifiers to look at sentiment analysis. For example, book reviews. You can train models to start learning whether the reviews are good or bad, and so it becomes easier for them to identify how books are doing. There's spam detection, the one I mentioned earlier, and then even for classifiers, you can use a multitude of different types of machine learning models. You can use the traditional bag of word models, which basically look at word frequencies, either a single word or a couple of words put together, which are called bigrams, or more like triple words. But the more words you put together to look at the frequency, then the more computationally intensive is, because you have many more complications. It's basically what you're doing is constructing a matrix of all the words and their frequency for each document, and using that to train the model. And usually you have to normalize, actually almost always you have to normalize your words so that words like the word the, for example, which is very common in all documents, is weighted low. And one algorithm to do that is called term frequency inverse document frequency, which makes words that are more significant stand out. More recently, there's been deep learning classifiers, which instead of just depending on word frequencies, they start looking at sequences of words. In these models, the words are represented by numbers. So you take each word and represent it by a vector, and the vectors can have a multitude of different dimensions. So for example, if I choose to use 200 dimensions, all my words will be translated to 200 dimension vectors. And then you can use that for your feature set for your model. And there are many ways to convert words to vectors, and this process is called word embedding. And it's usually you can do this in an unsupervised way, meaning that you don't need label data to translate words to vectors. One recent way that this was done or developed, in a decent model that was developed recently by Google, is called Word2Vec, and it uses a shallow neural network, and it allows you to construct semantic similarity of the different words, and I'll show you what that looks like in our experiment. So here what we're doing is translating our words into different vectors, and the model looks at the you can tell it like how many words before and after to look at when it's constructing the vectors for the different words, and it learns what the words mean based on the words that it's surrounded by. That's the main idea behind word2vec. So going into our experiments, so we have many reasons where we want to use classifiers on EHR. Here are some examples. One of them is for research, where we want to identify a set of patients for a specific research study, or for you could also do that for population health studies if you want to automatically do chart reviews in the EHR to look for an incidence of a disease. If you know your denominator if you can predict or estimate your denominator from the EHR. You could also use it for things like clinical decision support. So you could use the output from a classifier into a clinical decision support tool. These are only a few examples, and I'm sure many of you can think of many others. So in our case, one of the first use case that I'm going to mention today is pulmonary embolism, in which we need the altered mental status, which is important in this validated instrument called the Pulmonary Embolism Severity Index, or PESI for short. And you can see from the guideline here that the altered mental status adds significant points to the risk index for risk stratifying patients with pulmonary embolism when they are seen in the emergency room, which eventually impacts their treatment afterwards. So it helps people make a decision on whether they should be admitted or observed carefully or just discharged home. Here's another paper showing the importance of history of altered mental status, or syncope in this case, as part of the symptom set that you're looking for in pulmonary embolism. The question that we asked ourselves is, can we use artificial intelligence to identify patients with altered mental status based on their clinical notes? Because that's typically not always indicated in ICD-9 codes or ICD-10 codes. And so possible approaches are either to use the traditional NLP pipeline, which identifies keywords and then label those as yes or no, or you could use machine learning models like we're doing here. Even in machine learning, you can either use the traditional bag of words models that I mentioned earlier, or deep learning text classifiers. So the way we went about this is we got IRB approval to get a bunch of notes from the EHR, and specifically emergency department notes. So we wanted to be very specific to the emergency room. And the idea is that we had a large number of patients who we knew had a high likelihood of altered mental status based on the diagnoses that they were given during that emergency room visit. And we picked 2,000, which we labeled as controls, which never had, according to their EHR, never had any of the signs or symptoms of altered mental status by ICD. We also enriched the data with deep vein thrombosis and pulmonary embolism patients, so that we wanted to look at we wanted to teach the models to look at altered mental status in the context of pulmonary embolism. So although this is based on ICD, the initial set, that's what we asked for from our data analysts. We had to then go in, and I'll explain that in a minute. Actually, I'll get to that, the labeling of the data. So where we got the data is from our research data warehouse. So we have this research data warehouse at MESC where we put all our EHR data. We extract that from Epic. The other unique thing about our research data warehouse is that we also put clinical text notes within it, so that we can use that for machine learning task or other NLP tasks that we do here at MUSC. Usually the text notes are kind of messed up when they are stored in Epic itself. So you have to do a transformation process, and we put the notes together like jigsaw puzzle and put them in the RDW as complete notes. The notes are notes that are very large are segmented into multiple notes. So in the long, ultimately then we have our notes in the research data warehouse, and then we can do research on those. When I request the set of notes from our analysts, they give them to me in the form of a data mart that I can use then to access either from R or something else. Okay, I mentioned briefly the labeling process. So because we don't trust the ICD codes very much, we tried to label as many of the clinical notes as possible that we got from our data analyst. So we ended up with 9,000 notes from 4,000 patients, and we parsed those notes. So it's tricky to parse the notes because they're not all uniformly segmented the way they should be. So I parsed the notes looking for things like different beginning and ending of segments like history of present illness, or chief complaint, or physical exam with a colon after it and a bunch of spaces. So using that crude method, we were able to segment the majority of the notes. So 8,000 plus notes we were able to segment. And so we were able to identify the history of present illness out of these 8,000 notes. And what we did is we exported them into REDCap, and we asked the clinical people on our team, including myself, to go in and review the history of present illness and check whether is it AMS or it's not. Does it have altered mental status in it or doesn't? And so we looked for things like loss of consciousness, syncope, patient was found unconscious, all of these different types of ways that you can say loss of consciousness. And we gave them a very specific guideline, which we put in REDCap, like if you detected disorientation, lethargy, stupor, confusion, coma, any of these things were considered as a positive label. So after labeling, we ended up, because it's labor intensive, we ended up with 1,130 patients. And we had, sorry, not patients, 1,130 notes with history of present illness. And these belong to 858 patients. And they were divided between 400, almost 500 notes with altered mental status and 600 without. And we also calculated the inter-rater disagreement using, we looked at only 100 notes. For two people looked at 100 notes to see if there's any discrepancy between the reviewers, and it turned out there were a few discrepancies, and the Cohen's kappa was 0.94. Not, it was pretty good consistency. So the software tools we used were SQL Server for the data mart. We used REDCap. We used R for doing our statistical or our machine learning models. And this was built on top of Python libraries. And I'll explain that in the next slide. And we used GPU hardware. So the deep learning software stack that we used was, we used NVIDIA GPUs. And to do that, you have to install this thing called the CUDA library. And from that, then you can call the library from Python. But before you do that, you have to install also a low-level library that's usually compiled from C code, which is more efficient and has binary code, which is compiled to be accessed from Python. And so the library is called TensorFlow, and it was developed and open sourced by Google. And then on top of that, you have a standard interface library called Keras, also developed for Python. But there are also libraries in R that you can install in R that actually, act as an interface to Keras in Python. So the first step is you have to install Python, like either an Anaconda or something, the Anaconda distribution or something else, and then you can install the R packages that communicate with the Python libraries. And the code looks something like this from within R. So here's a very simple example, building an artificial neural network. So it becomes really very easy, which, I've done programming in the past. I've done C and C++, but to develop a program with machine learning in C or C++, it takes a long time. So with the R libraries, it's become a lot easier. It's sort of like to build neural networks, it's like playing with Lego blocks. So so you can like put your decide what layers you want to have. Use the hyperparameters for the layers, choose what regularization you want for each layer and things like that. And then also it becomes very easy to train the model. You can use different hyperparameters there. And here, for example, you can see that there's a validation split of 0.1, or 10% of the data was used for validation. And then eventually you see it right in front of you, starting to learn with each cycle what the loss function looks like as it goes through different what we call epochs, which are the each epoch is a cycle in which the training vectors are updated. So for our models, we use the traditional machine learning models as a baseline. So we use naive Bayes and many others. I'll show you these in a minute. But for the traditional bag of words, of course, you have to use a different text processing procedure. So we lowercased everything to reduce the number of features that we have. We removed punctuation. We stemmed the word so that you don't have a huge word matrix. And then we use TF-IDF, which is term frequency inverse document frequency for normalizing the data for bag of words. We only use single word frequencies, so unigrams, not bigrams. A colleague of mine tried bigrams and didn't find any improvement in one of our experiments, so we didn't use it for all of immense status. Whereas for the deep learning models, we use word embeddings, and so the processing is slightly different. It only involves lower casing and replacing periods with ends of sentences, so that the model starts recognizing when the sentence begins and it ends, and where the words fit in the models. And then after the appropriate processing for each, we pass the data to the different models. Deep learning models for one, and then the bag of word models in another. Okay, so here are the different bag of word TF-IDF classifiers that we use. We use naive Bayes, lasso, single decision trees, random forest, support vector machines, and finally artificial neural networks. But we use, in this case, we use a simple multi-layer perceptron, or MLP, for looking at bag of words feature. So it's not quite deep learning. It's obviously a shallow neural network just to look at bag of words features. So for the deep learning, we used something called the convolutional neural network model, which is very commonly used in image processing, and the example I showed you at the beginning. It's based on neurology experiments on how the different neurons in the brain recognize different features in layers. As I mentioned, like recognizing edges first and then other features and so on. So we can do the same for text sequences. So the models can recognize different word embeddings, and then from there, passing it through different layers to recognize other features, and eventually giving you an output, a yes/no output, or other multi-class classifier output. So we're not the first to do this. This has been done quite a bit in the industry. For example, in sentiment analysis, we adopted this model from a published example. We modified it slightly to apply to our EHR data. So we used instead of using we used both trained and pre-trained word embeddings, but in separate experiments. And I'll show you the results of those in a minute. So the word embeddings that we used were, for the pre-training, we used Word2Vec, and since it's unsupervised, we used all the 8,000 notes that we had. So I trained all of them, all of the history of present illness notes on Word2Vec. It's a shallow neural network that, like I showed you in the previous, in one of the previous slides. So it takes time, but not a huge amount of time on a GPU machine. And we translated our words to 200 dimension vectors with a context window of 5 words before and 5 words after each word. There was, and the other type of word embeddings we use is plain word embeddings without any pre-training. And so we compared both the pre-training and the Word2Vec training as different models. And then, so each word, like I mentioned, is represented by a number of an n-dimensional vector. And just to show that the Word2Vec works, we, instead of, so we mapped our 200 dimensions to 2-dimensional space, just to be able to see if the clustering is working, or word similarity is working. And in fact, it does work, and you can see things like, the words that tend to appear in the beginning of the note are clustering together. Same thing for recurrent mental status, that kind of thing. And then hours, lasted minutes have similar meaning, so they cluster together. And here's the structure of the convolutional neural network we use. So there's the input layer, then the embedding layer, where we use the weights, either use the weights from the Word2Vec model or just left them alone with random initialization for the untrained model. And then we used a regularization with a dropout of 0.2, and then the convolutional layers. And we use different window sizes, which window sizes basically tell you how many words to look at the same time, and then summarize them in what's called global max pooling. And so we used those in parallel with a window size of 3, 4, and 5. This is the model that I showed you earlier, was described in the literature for sentiment analysis. And then you merge the output from these into another layer, which and then into a dense hidden layer of 200 nodes, and then again regularization with a dropout of 0.2, and then finally a sigmoid activation. Sigmoid is the one that you use for a binary classifier. And we used, since we didn't have a ton of data, we used what I mentioned earlier, where we used k-fold for training testing. So in each of these 5 cycles, we used the test data as the holdout unseen data set for the training. And so we could fairly use it for estimating how the model works. And then we averaged the results, or pooled the results from all of them. We also wanted to look at how accurate the ICD codes were. So we took the ICD codes for AMS code, for AMS, and we looked at the labeled set that we had, the 1,100 records. It turns out the accuracy from ICD codes is 81%. So the other thing we looked at is to look at the characteristics of the different documents in both in the positive and negative, And I'm going to start going quickly because I think we're running out of time. So that's based on word frequency. And then we also looked at the random forest variable importance. You can see words like confusion showing up as important, altered method, because these are the words we looked for when we were reviewing charts. And the interesting thing is that words like pain, you can see here that pain negatively tends to be more common in the non-altered method status, because if they tell you they have pain, then they're not likely to be altered. So it's also an important variable. So finally, the result of this specific experiment is that in the bag of word models, we got pretty good results. The best model was an AUC of 0.975 with the random forest. So it's already very high. It was hard to improve on that. Yet in the machine with the deep learning models, we did slightly better. So we're getting an AUC of almost 0.99. But there was no difference because it's so close to ceiling. There was no difference in word to vec versus unpre-trained models. So here's just the metrics for all the different models. The interesting thing to point out here is the number of cycles that it took the word to vec models was less. So you can see that the untrained models took around 30 cycles. So we put an early stop, as soon as the loss function reached a plateau or a minimum, then we told the model to stop after 10 tries. And so it turns out that if you pre-train the models using unsupervised data with word to vec, they tend to stop, so it tends to learn faster. And this is what the learning curve looks like. So, so the other thing we looked at is there's quite a bit of motivation in research to create de-identified sets of notes that you can use then for research without worrying too much about privacy and security and confidentiality. So we did an experiment to see what would happen to nodes in terms of their fidelity of the information and utility for machine learning when you remove all the identifiers from them. Are they still useful? And there are several ways to do the identification. We collaborated with one of our experts in NLP, Stefan Maestri, who's published a lot in the area of de-identification. So we used one of his open source pipelines to de-identify nodes. And we ended up for this experiment, we used, out of the 1130 nodes, we used 1113 nodes of history of present illness, and we were able to replace a total of 1,700 PHI tokens. Things like unit name, which were the most frequent, ages above 89, which are considered PHI, dates, provider names, patient names, and so on. So a total of 1,800 almost. So what does this do to your machine learning models? Pretty much nothing. So the machine learning models perform just as well with any of them, actually. They all, even the random forest and all the rest, removing the identifiers doesn't affect the model. So another use case that we looked at was to look for acute ischemic stroke and MRI reports, and we used very similar models for that. And the motivation there was for recruitment to find patients from the MRI report, for recruitment into our stroke registry. Another motivation here was to look at estimating the incidence of acute ischemic stroke. As then acute here is a keyword, so you want to identify them in the acute phase so that you can use that for incidence. So we used MRI reports. We labeled. We worked with a collaborator from a visiting professor from Korea who worked with us to label the notes. We ended up with 958 notes. MRI reports there. And then we had very similar results and performance between deep learning and bag of word models. So our collaborator from Korea, we've published the first set of, what we did actually is looked at data from Korea first, because this person, Chul Ho, he came with the identified data from Korea that we tested before we got IRB approval for the MUSC data. And then, so the natural question then would be is, what's the difference between the Korean data and the MUSC data? So we did experiments on that. And in this case, then, the word frequencies start looking more interesting. So if you look at both data sets, you'll see that there's a lot of positive words in the Korean. By the way, in Korea, they also use English language to transcribe their report. So it was, we didn't have to do any Korean to English translation. So it turns out that the important words in the MUSC data are more diverse, but they have different weights for Korea. And same thing for the negative words. But there are also cases where words cross the boundaries between positive and negative. So the predictions then, so we thought, what would happen if we train the models on the Korean data and then use MUSC as test data? And it turns out the models don't perform very well when you do that. And then we did the reverse, and we believe that the MUSC data is more diverse and therefore is probably better for training general models. So we got slightly better performance. In fact, with the deep learning models, especially those pre-trained with word2vec, we got pretty good results by, and this was pre-trained only on MUSC data, but it turns out it helped the classifier for the Korean data. So then what we did is we mixed the data from MUSC. So we trained it not just on MUSC or just on Korean. We trained it on both MUSC and Korean data. And of course, that's the best solution. So the more data you have, the better, and the more generalizable your model is. And so the combination data on MUSC has pretty high results for both bag of words and deep learning models, and same thing for the Korean test data. So in conclusion then, the labeling of the data is time consuming for supervised learning, but we had to do that, but that's why we didn't have thousands of records to do that. Word embedding preserves the sequence of the words. We think that's why deep learning models do better, because you can not only look at the word frequencies alone as features, but you can start looking at how the words are arranged in a sentence, which obviously give you better features. So we went back and looked at some of the sentences that the machine learning models missed, and it turns out we're missing some of those, what we're calling deep negations. A sentence like denies shortness of breath, chest pain, and then they say loss of consciousness. So you can see it's quite a distance between the word denied and loss of consciousness. So some of these were missed, not all of them. And so one way to get around this is potentially to use negation as a part of the pre-processing. We haven't done that yet. And we think that our models performed really well because we're looking specifically at symptoms. We're not looking at outcomes. Outcomes predictions also depend on patient. More typically, machine learning models are used to look at outcomes, and where you have many other variables and not definite outcomes. So for a very focused task like this, we did very well. So I mentioned some of the limitations already. So we did the Alterman status, at least we did at one institution. So we're trying to work with Christiana Care to look at how models generalize. The nice thing about the Christiana project is that they have also a different EHR system. So their notes are going to be written differently. So the question is, how well do the models generalize across our institutions? Notes are templated, and that also will impact how well they generalize, we think. We'll see. So far, we're limited to only history of present illness. We'd like to test our models on physical exam as well. Preliminary analysis shows that they do very well also on physical exam, but we have yet to show that data. I think this is, I'll stop here and we'll take questions. So we've been working with a lot with COBRE data and some help from the CTSA and the Delaware grant as well, Smart State funding as well. And these are our collaborators for MUSC. That's it.
Questions?
Yeah, a quick question. When your researchers labeled those notes, does that mean they had to read every single note, or was every note read? You said there were 10,000 notes additionally identified.
Yes. Okay. So let me go back to that slide. Here we go. So we started out with 8,000 notes that were not manually read, and we then took out of those 1,100 notes that we read manually, and we only read the history of present illness. So it wasn't a huge, it's not very burdensome, but still, reading 1,000 charts is no small task. We didn't read the whole chart, just the history of present illness. So we were able to do that. It takes about 5 minutes to 10 minutes per note, and we divided this between 4 different people, and we were able to get that done in a couple of weeks. Is that what you're asking?
Yep, that's it.
Yeah. Did you consider using recurrent neural networks at all rather than convolutional?
Yes. In fact, we did. We tried using recurrent neural networks. I tried LSTM and GRU as 2 examples which are supposed to do well. The reason you would want to think about recurrent neural networks is because they work well with sequences. They typically used in sequence predictions. So we thought they might work well with word sequences. But one disadvantage with them is that they are much, much slower than convolutional neural networks. And in our hands, they yielded very poor results for some reason. I didn't report on them is because we're still trying to figure out exactly why they aren't working very well. Once I confirm that, in fact, they're not working very well, we'll probably publish on that as well. So we're still looking at different ways to different network architectures to look at. I showed you the model that we used is using convolutional networks, convnets in parallel. We're also looking at using them in serial or in sequence one after the other. Some people have reported good results with, for example, looking at EKG tracing, classifying EKGs with that. So we might try to use in serial as well.
Jihad, when you compare the Korean to the U.S. example, and you mentioned there might have been a difference because of diversity. Do you mean diversity of the symptomology or the patients, or diversity of the words used?
Yeah, I think what I meant is diversity of the words they use. The Korean, we think that the Korean data is less, they have a smaller, how do I say this, less ways in which they say a person has acute stroke than we do at MUSC. And the notes at MUSC tend to be slightly longer. We tried also matching the notes by length, and that didn't help very much. So we're not exactly quite sure what's going on, but we think that it's due to diversity of ways that they report their MRI reports.
Gotcha. One more question. What's your like long-term vision for how these methods are utilized, either in research or in practice?
So one of the things that we would like to do is actually take the altered mental status project to its you know, the reason we started this was to use it for the pulmonary embolism severity index, the PESI score. So we're thinking of if we get funded to work on the machine learning, the next step is to get funding to actually go ahead and not only develop the machine learning models, but also putting them in practice using, you know, HR7 Fire or something where you can get data out of the EHR, have the models perform outside the EHR, and then feed the results back into a clinical decision support tool and have it display within Epic or to help clinicians make, you know, to automatically calculate the PESI scores for physicians that help make a decision. So that's one area we'd like to use. The other one is for the COBRI project for the Restore grant that we had, the Restore database, where we want to enhance recruitment. So we're thinking of doing a similar process where we would automate the detection of acute stroke and then send an alert to the research coordinators so they can recruit patients to put them into our registry.
Ask a question?
Yes.
Do you have any thoughts as to why the random forest performed almost just as well as the neural network?
I'm sorry, your question is why do we think it did that?
Well, the random forest, I'm not that familiar with all of these methods, but the random forest, I believe, is less intensive a method, and it performed pretty well. I was just wondering if you had any thoughts as to why that method was performing pretty well.
Yeah, I mean, so random forests are commonly used in text classification, and they do tend to do very well. Actually, I mean, in a previous experiment we used with lupus in the past, they also did very well, and they certainly do better than single decision trees, at least in diverse data sets, and better than naive Bayes. And so I was not surprised, really, that they did well. We also had very good results with support vector machines. Both of these models, random forest and support vector machines, did better than a shallow neural network when you're looking only at word frequencies. But we were still able to beat that with the deep learning models. So I don't have a good answer for that. All I know is that from experience, random forests work well with the classification algorithms.
Thank you.
Other questions? Go ahead.
So usually there are like combined methods with supervised and unsupervised. So for example, they use clustering first, so to create the labels like cluster 1, cluster 2, and so on, based on some distant metric, Euclidean or whatever that can be. And then they attach these labels to the original data, and then they use these classification methods like SVM or random forest or so on. So have you guys tried that kind of like combined methods and see the performance?
Yeah, no, we haven't. And that's a good idea. One thing we're thinking of doing, we have a couple of researchers who are interested in working with us on doing more classifiers, for example, in the area of liver cirrhosis, and another one looking at op notes in the operating room to see if we can find surgical errors. And there, what we're doing is we're going to try by clustering the data using only ICD codes, and then train the models on those. and then see how they perform on the rest of the data. So it's kind of like clustering, but with ICDs. We haven't tried clustering based on words. We thought about it, but we haven't, gone down that path yet.
Go ahead, Mitch.
I have one more question. And this is just kind of just about methodology involving word to vectors. Is this sort of work, is it always necessary to generate those vectors using your study corpus, or could you use, say, a really gigantic corpus, say like all Wikipedia, that maybe somebody else has already done?
Right, very good question. So there are word-to-vec models you can download that are already trained. One is on Wikipedia. One is on, there's a couple of them that were trained on all of PubMed, in fact. But I think we tested one of them, at least one of, I have a student working with me from USC, and he tried the one from, I think the PubMed one, and it's not performing very well in his hands, but we haven't completely confirmed whether it's because it's due to being trained on PubMed versus being trained on our data. I would imagine that these are going to be context sensitive. The way people say things in an electronic health record is different from the way they publish the records in the EHR, although there are still many words in common, like for example, the common English words like the and what and whatever, but these are not going to be your significant words in determining the features that you're interested in. So we thought we would actually train the word-to-vec on our EHR data. Now, I still don't have a good answer whether that's a necessary thing to do or not, because as you saw, it didn't add much to the learning, to improve learning. But because we're very close to ceiling, we aren't able to tell this. It would be interesting to test those models against each other using other experiments like the cirrhosis one that I mentioned, and to see if pre-training helps any.
Thank you.
Great.
I have one question. So I'm a clinician, but I'm very limited on some of the methodology, and so forgive my ignorance about this question, but one of the things that you talked about was the long-term goal is to be able to maybe create a clinical decision support tool. You gave the example around, obviously you talked about both DE as well as altered mental status, acute ischemic stroke. One of the things I'm curious about is, are any ongoing projects right now to kind of combine the methodology you've talked about with some of the focus from the sepsis movement around early warning scores, to use laboratory and vital sign sort of information that comes in sort of one type of data with sort of text data and free text data, to combine those two to sort of help clinical decision making?
Yeah, I did some searches of the literature and found that yes, people are using machine learning output and feeding it back to clinical decision support. I'm not quite sure whether they're using deep learning models yet. I'm sure it will happen at some point. So to answer your question, yes, people are using machine learning for clinical decision support. And it does tend to be like, as you're describing, where you're using known structured data, primarily, like whether they have, for example, hemoglobin A1C above a certain level or not, and whether they had an ICD code show up in their history or not. And I think some people also have started using some text classification, but I can't swear to that. I can't remember in my literature review whether I came across that or not.
All right. Thanks again, Jihad.
All right. Thank you. Bye.